What are effect sizes and how to use them? In this video, I will describe what an effect size is. Then I will describe two different effect sizes commonly used when you're comparing two means, and when each of those is most helpful. Finally, I'll describe how to use effect sizes to assess the practical importance of results, to compare results across studies, and to estimate the sample size needed to detect a certain effect. There are many different types of effect sizes in statistics. This video is focusing specifically on an effect size used to compare two means. In this context, an effect size is a statistic that quantifies how well a treatment worked or how different two groups are on a specific dependent variable. A large effect size suggests a treatment was very effective and/or two groups are very different on a specific dependent variable. Obviously, a small effect size would suggest that a treatment was less effective and that two groups are not very different from each other. When a study is comparing two means, when it's using a t-test or ANOVA post-hoc tests, there are two different effect sizes that are commonly used: the mean differences and the standardized D. Depending on the research situation, the mean difference might be computed as a sample mean minus a population mean, as is reflected by the top term, or the difference between one sample mean and a second sample mean. In either case, the observed mean difference is the difference between two means. Obviously, larger mean differences would reflect larger effect sizes. The second option for measuring effect size is the standardized D. As is reflected here, there are many different ways to compute the standardized D, but all of them are taking a mean difference and dividing it by some measure of the typical amount of variability in the data. Here again, a larger D would reflect a larger effect size. These different types of effect size tend to be more useful in different types of research situations. For example, the mean differences effect size tends to be more useful in situations when you are more knowledgeable of the variable that you are trying to measure. If I told you that after a treatment, you would get a 10% increase on your next exam score, you probably have enough background knowledge on what it means to have a 10% increase in score that you would deem that increase to be large enough to be important. In other situations, that might not be the case. If you were measuring performance on a task and you were measuring how long it took people to perform the task, and after a treatment, their performance went down by 500 milliseconds, if you do not have a lot of knowledge on that task, you might not know whether or not a 500 millisecond decrease in time is large enough to be important. In that situation, a standardized D might be the better choice. I'll have some examples of this in the next coming slides. For the rest of the video, I'm going to provide examples of how you can use effect size. Specifically, I'm going to talk about how you can assess the practical importance of an observed effect using effect size. I'm going to talk about how you can compare observed effects across different studies. And I'm also going to talk about how you can estimate the sample sizes needed to test a specific hypothesis. A really important function of effect sizes is their ability to help you assess the practical importance of an observed effect. You can do this using mean differences or a standardized D. Here I'm going to describe how you might do that using mean differences. If a study found that a treatment would lead to a mean difference of an increase of an exam score by 10%, again, as we indicated earlier, most of us would have enough background on what a 10% increase would mean that we would deem that to be important. If a study found a mean difference of a decrease of 58 cents per week on a paycheck, most of us probably wouldn't deem that to be too important. If a third study found a decrease of 11 milliseconds in reaction time, a lot of us probably wouldn't have enough background knowledge to determine whether or not that's an important decrease. As we learned earlier, assessing the practical importance of an effect using the mean difference approach is really most helpful when you have a lot of background knowledge. You can also assess the practical importance of an observed effect by using the standardized D. The advantage of this approach is that there are guidelines that help you interpret the size of an effect. If you get a D close to 0.2, that's considered a small effect. Something close to 0.5 would be a medium effect, and something close to 0.8 would be a large effect. Now, in most situations, medium and large effects are going to have practical importance. A small effect can have practical importance as well. It just depends on the research situation. For example, if there was a new treatment for a type of cancer that there was no other treatment for, even a small effect would probably be important. Here, I'd like to highlight an important difference between the mean differences approach and the standardized D approach to measuring effect size. The mean differences approach provides a measure of effect size in raw score units. It's a 10% increase in exam score. It's a 58 cent per week decrease in money. It's a decrease in time of 11 milliseconds. All of these are in the actual unit that the DV was measured in. The standardized D is different. It provides a measure of effect size in standardized units or standard deviation units. A D of 0.8 means an increase of exam score of 0.8 standard deviations, and this would be deemed a large effect. A decrease of 0.08 in terms of D would be a decrease in weekly income that would be deemed very small. And a decrease in reaction time of D equals negative 0.45 would be a medium effect and a decrease of about half a standard deviation in terms of time. Effect sizes also help you compare observed results across studies. While it's possible to compare effects across studies using a mean difference approach, you're quite limited in what you can do. For example, in study 1, an increase of 5% in exam score was found. In study 2, a 7% increase was found. You'd be tempted to say that the 7% increase is better than the 5% increase. And it might be, but that's only true if the two studies are very similar in how they were done and the type of test they were using. So you can compare effects across studies if the DV being used is similar and the situation in which the DV was collected is similar. In study 3, we really can't compare its results to either the results from study 1 or study 2 because it's using a different type of dependent variable. Now you might be able to convert that to a percentage, but again, then you're no longer using the mean difference. The key point here is that it's very difficult to use a mean differences approach to compare results across studies. Studies have to be using the similar dependent variable, they have to have a similar study design, and something I haven't talked about yet is they have to have similar variability in the dependent variable. And I'll illustrate that in my next slide. Using a standardized D is probably going to be the better choice when you're trying to compare results across studies. I'm going to illustrate this point by talking about the 3 different studies we discussed previously. Study 1 found a 5% increase in exam scores. If we convert that 5% into a standardized D by dividing it by the standard deviation in its data, you'll find that you got a D of 0.45. That's a medium effect. If we do the same thing for study 2, which had a 7% increase, we'll find that its D is a 0.35. It had a smaller effect size in terms of standardized D. And the reason why is its standard deviation of scores in that second study was quite a bit larger than that in the first study. Perhaps that test was more difficult. And so comparing the 5% increase to the 7% increase was a little bit of an unfair comparison if you were using the mean difference. However, the standardized D adjusts for this. And so we can see that the first study had a larger effect than the second study. Perhaps the intervention that led to the effect in the first study was a little bit better or more effective than the intervention used in study 2. And the only way we would know that is by using the standardized D to compare the effects observed in the 2 studies. Study 3 shows the same point, but perhaps more dramatically. We had a completely different dependent variable. So using the mean difference effect, we couldn't make any comparison at all. But after we convert this data over to a D, we will find that it had the largest effect size. This might be the most effective intervention of all 3. The key point here is that standardized Ds are the better choice when comparing effects across studies. Another important use of effect sizes is to help us estimate the sample size that's needed to test a specific hypothesis. When you're planning to perform a study, it's important to recognize that smaller effects are harder to detect statistically, and therefore they're going to require larger sample sizes. If you know that a given study is likely to yield a small effect, you'll need to have approximately 400 participants in each of your groups. If, however, you anticipate an effect size that is medium, something close to a 0.5, you might be able to get by with 65 participants per group. If you're lucky enough to be looking for a large effect, a 0.8 or larger, a sample size of 25 per group would be appropriate. Now, how do you know what effect size you're looking for? Often you don't know, but sometimes you can know by reading the literature. If you're designing a study that is similar to a study that's done in the literature, that would be a good guess at the effect size you might anticipate. Another way of thinking about this is that maybe you think, I'm only interested in medium or larger effect sizes. And if that's the case, then you might be able to say, I want 65 participants per group. If, however, you are thinking that a small effect would be important, then you're going to need 400 participants per group. You can also use effect size to evaluate a completed study. If you observe a large effect size and it's paired with a high p-value, this is going to suggest that your sample size in that study was too small. In this example here, you have a p-value of 0.27. That p-value suggests that the data are consistent with the null hypothesis. You also got a d value of 0.66. That suggests that there is a medium to large effect size. These two statistics are inconsistent. The p-value suggests the effect is unimportant, it just happened due to sampling error. But the d suggests it's a medium-large effect. If you get two inconsistent results like this, in terms of the p-value and the d, that suggests that your sample size is too small. Be aware when you see this particular combination of p-value and d. A high p-value and a high d should suggest to you that you should redo the study with a larger sample size. If you're interested in learning more about effect sizes, here are a couple references to get you started. If you're interested in learning more about statistics, visit us at learnstats.com.